all, in this video, we are going to see about geometric transformations. Geometric transformation is a mathematical operation that maps points from one coordinate space to another, which means we can change the position, orientation, scale, or we can change the shape of the object. Particularly, it will be useful in manipulating objects, images, or 3D models, such as rotating an image, zooming in, zooming out, correcting the perspective, or stitching panoramas. Panoramas you may have seen in camera, mobile phones. And geometric transformation 2D. We have 2D geometric transformation as well as 3D geometric transformation. Here is the set of 2D planar transformations. The first one is translation, then Euclidean, similarity, affine, and projective. We'll see all the five types in detail now. Translation. Translation means it is just moving a point by fixed amount in the x and y direction. Okay, so if I have a square shape, if I have a square shape, I'm in the coordinate or maybe 1 comma 1. I may want to move the same to 2 comma 2. Okay, assume this is 1 and 1. The coordinate is 2 and 2 means, so I have to move the same square to the another coordinate. So just moving a point by fixed amount in the x and y directions. We have to move in the x direction as well as in the y direction. Okay. So see this diagram. If we have original x and y coordinate and the translation x and y is represented as tx and ty. So if we have a point x and which is nothing but x comma y, we are representing in matrix format as xy. Okay, and the translation vector, how much point we have to move is represented as tx and ty. Okay, so t equal to tx and ty. Then translating the point is represented as x plus t. Okay, so here x plus tx, again y plus ty. So x is nothing but xy plus the matrix addition tx plus ty. So xy plus tx will become x plus tx. Similarly, y plus ty. So this is before translation. This is after translation. Then instead of writing this x dash equal to x plus xt, we can write also as x dash equal to I t x bar. Okay, this represents the homogeneous. Normally, this represents inhomogeneous. Inhomogeneous, we know if we have a point x and y, we will convert just as x equal to x and y. If we want to represent the same in homogeneous way, we will add 1 at the last. Okay, so this equation represents inhomogeneous coordinate, this equation represents homogeneous coordinate. Okay, where I is the 2 cross 2 identity matrix. How the matrix will be now? 1 0 0 1 tx ty. We know t is translation vector, so tx ty, and this is x bar. X bar, we know xy1. Okay, so now you can see it is a 2 row 3 column 2 cross 3 matrix. Okay, so using a 2 cross 3 matrix result in more compact notation, which is not that easy to perform manipulations. So what we are doing means we are going to convert it as a 3 cross 3 matrix as a full rank matrix. How means we are just appending a 0 transpose and 1, where 0 is nothing but a 0 vector. So 0 is nothing but 0 vector. 0 transpose means 0 and 0, and additionally we are adding in 1. When compared to 2 cross 3 matrix, this 3 cross 3 matrix is better for performing chain transformations using matrix multiplication. Okay, if the dimension is 3 cross 3, which is if the dimension is m cross m or n cross n, which is nothing but full rank. 2 cross 3 is not full rank. 2 cross 2, 3 cross 3 is a full rank matrix. The full rank matrix will be easy to perform matrix multiplications as well as it will be easy to perform chain transformations. Okay, so we are converting 2 cross 3 to 3 cross 3. So the transformed matrix is represented as x bar dash equal to 1001 translation tx ty, and the 0 transpose 0 vector is transposed as 0 0, and finally we are adding 1. So this 3 cross 3 matrix along with the x bar, okay, will result in 3 cross 1 a value, okay, which is nothing but the translated one, right? So if you want to represent the normal 2D translation, then we have to represent this equation. If you want to represent in a homogeneous way, we can either use 2 cross 3 or 3 cross 3 matrix, but this 3 cross 3 matrix is preferable. Okay, on performing this operation, the normal 2D translation will be translated into projective space. Then Euclidean transformation. Euclidean transformation include translation plus rotation. What we know, translation, the translation can be done either moving left, moving right, moving up, or moving down. If we have a square, we can move to left, move to right, move to up, or move to down without changing any orientation, right? So here, rotation means we are spinning the object around a point, usually the origin. It will have some angle. You can see that if the original square is this, the angle here is 90 degree, 90 degree, 90 90. After translation also the angle is preserved. But in case of rotation, the angle is not preserved. Okay. So the Euclidean transformation is nothing but rotation plus translation. This is also known as 2D rigid body motion or 2D Euclidean transformation. Okay, we are preserving the distances, we are just only changing the angle, the length will be same. Okay, just only the angle is changed, so we are calling the, so we are saying the Euclidean distance are preserved. Okay, same the previous one, instead of identity matrix we are going to represent the rotation matrix. Okay, so x dash equal to RT of x bar, where R represents the rotational matrix and T represents the translation vector, which we know already. So since I is identity matrix, we know 1 0 0 1, diagonal is 1, remaining elements are 0. Here we have to represent how much amount of rotation we have to perform. We can perform 45 degree of rotation, 90 degree of rotation, 180 degree of rotation, or 360 degree of rotation, right? So we have to represent how much angle I have to rotate. So for that, the rotation matrix is represented using cos theta and sin theta. So cos theta minus sin theta, cos theta. This is the rotation matrix. So if theta is equal to 0, then the point doesn't rotate. If theta is 90 degree, it rotates clockwise. Now let us see an example. Hope you are clear with this equation. X dash equal to R T X bar, which is the homogeneous representation. Here this represents inhomogeneous. Okay, with nothing but a real space representation. This is a projective space representation. Real space means what we are drawing in a paper is real space. What we are drawing in a computer is a projective space. Okay, so let us consider the homogeneous point x equal to 1 comma 2, when it is converted to x bar 1 2 1. Okay, so the normal point 1 2 is written as 1 2 1. I'm going to take the translation value as, sorry, I'm going to take the rotation matrix. So cos 90 degree minus sin 90 degree, sin 90 and cos 90. You can substitute the value. Cos 90 is 0, sin 90 is 1, minus sin 90 is minus 1, cos 90 is 0. I'm going to take the translation value as 3 and 4. So as per matrix, we have to combine R and T. So R is 0 minus 1, 1 0, and T is 3 and 4, right? So as per formula, RT of x bar, right? So RT matrix we have found 0 minus 1 3 1 0 4, and x bar is 1 2 1. So the dimension is 2 cross 3 and 3 cross 1. On performing matrix multiplication, we will get the resultant matrix as 2 cross 1. This you know, 0 into 1 plus minus 1 into 2 plus 3 into 1. Similarly, the next row resulting in 1 and 5. So the transformed point is 1 and 5. The original point 1 and 2, now it is rotated 90 degree clockwise and translated by 3 comma 4, which is resulting in a point 1 comma 5. Okay, so 1 comma 2 can be translated as well as rotated using the equation x dash equal to RT of x bar. Okay, at a time we can perform translation as well as rotation. So the next one is similarity transform. Similarity transform means it perform translation, rotation. In addition to that, it can perform scaling. Okay, translation means just we are moving the shape to the new position. Rotates we know. Scaling means we can change the shape. The normal square can be enlarged or it can be shrink. This concept is known as scaling. Okay, so it is also known as a similarity transform, right? So similarity transform, it is also known as a scaled rotation. It can be expressed as, so we know r is used to represent the rotation, t is used to represent the translation, s is used to represent the scaling value. So the matrix is x dash equal to s r t and x bar. Okay, so this t is a translation vector. Tx and ty represent the translation. So instead of this s, r, I am going to represent a minus b and dA. Let us see an example here. So what matrix we have written? A minus b, b, a. Right? So a minus b, b, a, tx, ty. Oh my god. Sorry. Okay, see the previous matrix A minus B, B and A, Tx, T1. So I'm going to take A as S into cos theta, B as S into sin theta. Because the rotation matrix is, we know it is cos theta and minus sin theta. Here sin theta and cos theta. Right? So A is S into cos theta, B is S into sin theta, and Tx and Ty are translation component. Okay, we are going to consider a point 1 and 2, and we are going to perform a scaling of value 2, which means if the square size is 1, we have to enlarge into 2. Okay, so if it is in the if the length is 1 and height is 1, we are going to convert the length as 2 as well as the height as 2. Okay, so the rotation is 90 degree, translation is 3 and 4. See this example. As per the matrix, we have changed A as S into cos theta, B as S into sin theta. So the scaling value we have taken is 2, and the cos 90 degree is 2 into 0, that is 0. Sin 90 degree is 1, so 2 into 1, which is 2. We are going to apply within the matrix. So as per the matrix, A minus B, B, A. So A is 0, B is 2, minus B is minus 2. Again, we are representing the A as 0. The translation value we have given is 3 and 4, right? So we have applied in the matrix. X bar, we know inhomogeneous value is 1 and 2. Converting to homogeneous coordinates, we get 1, 2 and 1. So we can perform the matrix multiplication, so which is minus 1 and 6. What we are concluding now, the 1 and 2 is translated by 3 and 4 and it is rotated to 90 degree. We have applied the scaling of 2 also. This concept is known as similarity transform. Okay, so the next one is affine. Affine is translation, scaling, rotation as well as shearing. Shearing means we can change the normal square shape into, the normal square can be changed into a parallelogram. Okay, this is shearing x. So this is shearing y. Normal x values can be considered as shearing of x and shearing of y. Okay, this preserves the point, this preserves the straight line. Straight line will be straight line, but the parallel remains parallel. Okay, so we can change just the shearing. Those straight lines or again the straight lines. Here also they are parallel to each other. Again here also parallel to each other. Just we are making the square into parallelisms, right? So the matrix here is x dash equal to a x bar. The matrix A is defined as A00, A01, A02, A10, A11, A12. So as I said already, this performs translation, scaling, rotation as well as shearing, right? So we have to represent the coordinates. So 0, 1, 2, 0, 1, 1. This represents translation. Okay. So this entire 4 value represents rotation. So A00 and A11 represents scaling. This represents shearing. Okay. So the entire matrix is divided to perform all the four operations. So on applying this homogeneous vector, we'll get the value A00x plus A01y plus A012 because the last one is 1. Similarly, A10x, A11y, A12 into 1 will become the same. So I'm going to take an affine matrix 1 1 0 0.5 2 3. This represents the translation. 1 0.501 represents the rotation, and this represents scaling. 0 and 0.5 represents shearing. I'm going to convert the 0.41 into 4 1 and 1. On applying the affine transformation, I am getting the value as 6.514. So the 4 and 1 is converted into 6.514, which means I have applied translation of 2 and 3, and I have performed 1 0.5 0 1 rotation, and I have performed scaling. Scaling is 1, there is no change, and I have zero point 0.5 shifted. Okay, shearing of zero point 0.5. Then projective transformation, which is nothing but translation, scaling, rotation, shearing as well as perspective. So the matrix here is x bar into h bar into x bar, where h is nothing but a homogeneous matrix. It is a 3 cross 3 matrix. Let us see an example directly. I am going to take x equal to 3 and 2. On converting into homogeneous, we are having 3 2 and 1, and the h matrix is 3 not 3, 3 cross 3, h00 h01 h02. Similarly, h 10 11 12 h20 h21 and h22. On applying this matrix, we are getting a value rate 4.4 2.3 and 1.0. This is the translation, scaling, rotation, shade, and perspective way of transformation. So on converting back the homogeneous into 2D, this we already know in geometric primitives, we have to divide the third element with first and second element, which we can again get the 4.112 and 2.150, which is not same as this because we have performed rotation, translation, shearing, everything. So on converting back to 2D, this point will not be same as the transformed one. Okay, so now see the homographic matrix is 3 cross 3. So it is a combination of all the five. So this Tx, Ty is represented as H02 and H12. Right? The scaling represents the diagonal elements XX and XY. Rotation, as we know, first four elements. Shear X represents this. In case of shear Y, we want to know this value. H10 is shear Y. The value H10 represents shear Y. Perspective, the entire value is nothing but the perspective. Okay, that A, B, C, D, E, F, G, H1. So in general way, we can represent the H matrix as A, B, C, D, E, F, G, H, and 1. Okay, every element represents all the transformations. Okay, so here we are inhomogeneous. In order to get the inhomogeneous, what we are doing, we are dividing the third value. The third value is nothing but 1.07, which is nothing but the addition of the third one, h20 into this value, h21 into this value, h22 into this value. That's what we have represented here. Similarly, for y also we are getting the same, right? So the usually we know that inhomogeneous way is obtained by dividing the third element. So that's what represented here. This represent the first row, this represent the second row. So on dividing the third row, we are getting the inhomogeneous coordinate. So this is just a summary. We have seen five transformations: translation, Euclidean, similarity, affine, as well as projective. So we need to know the degree of freedom, right? So this is very important. This matrix we have seen identity along with translation, rotation along with translation, scaling, rotation along with translation. In addition to shearing, we are representing as A. All these combined along with projective, we are representing as H matrix. So this is the representation. Normal square can be represented as same but with some other moving position. The position alone changed. Okay, the position alone changed. This is nothing but rotation. Rotation means the length, breadth, everything will be same, just the angle is different. Okay, so here we are preserving the orientation. Here we are preserving the lens. Similarity means we know that it is nothing but a scaling. You can see this rotated square is somewhat small than this, right? So then affine, as I said earlier, it will just convert the square into parallelism. Project is completely different. It will maintain only the straight lines, angle, size, everything will be changed. Only the straight line, the line cannot be changed as zigzag. That is the only thing we can preserve here. Okay, so let us see the degree of freedom. So in case of translation matrix, we are representing Tx and Ty. So the degree of freedom is 2. In case of matrix, rotation matrix, we are having cos theta minus sin theta as well as cos theta. So we are having angle Tx, Ty. So the degree of freedom is 3 here. In addition to scaling, we are having scaled value, so it is 4, right? In affine, what we are doing. Yes, affine matrix, generally it is considering as all the values, all the diagonals we are considering, all the rotation values we are considering, we are considering the translation also. So how many elements we have? One, 2, 3, 4, 5, 6. So the degree of freedom here is 6. In case of H matrix also, we are having 9 values, A, B, C, D, E, F, G, H, 1. But the degree of freedom is represented as 8, because you can see all the transformation having the values 1 here. Translation, it is not affecting this one. Scaling, it is not affecting this one. Rotation, it is not affecting this one. Shearing is not affecting this one. Perspective, it is representing all the remaining 8 values. It is not affecting this one. So the degree of freedom here is 8. Okay, so that's all about 2D geometric primitives. Thank you.